I'm Ellen White. I'm a PhD student at the University of Southampton, and I'm going to present today some work that we've just had published around using machine learning for addressing like an ecologically important question. So hopefully it'll be of interest. Okay, just to check, everyone can see the presentation, okay? Yep. Okay, cool. We'll get going. So the title of my talk today is More Than a Whistle. The overarching theme is about using, as I said, a machine learning method to kind of address this ecological idea of how do we detect more than a single sound source from the marine soundscape. And my work applies it to delphinid conservation, but the theory behind it is that you could apply it to multiple different sound sources, and that'll become clear as we go on. I just wanted to draw attention to my co-authors. We have collaborated with not only researchers within our own faculty, but also Marine Scotland, the Scottish Association of Marine Science, and AFBI in Northern Ireland. And as I said, yeah, this forms a chapter of my PhD thesis, and the work is ongoing, but I'm just going to highlight this chapter today. So the ocean soundscape is, as we all know, becoming increasingly complicated. It's not just formed by the single signal or sound source that we are generally interested in our work. It has a lot of other components that overlap in terms of frequency and amplitude and how the signal is represented. And this problem isn't going away. This is becoming increasingly an issue where we have geophonic in terms of adverse weather becoming more frequent, and we have anthropogenic sound sources dominating our marine realms, particularly in the coastal waters. And the interaction between the biological sound source that we are usually interested in studying with these other soundscape components is an interesting question, but it's not something that we've been able to address using modeling. Typically, we have different data sources, such as AIS for shipping traffic, or modeling ecological patterns of movement with oceanographic data. So it got me thinking, is there a way that we could do this using a modeled approach? And machine learning obviously becomes quite a nice tool for that. So as I said, the typical pipeline or approach for like a species detection problem or classification issue is you take this single signal of interest, whether it be a fin whale or a blue whale, or as we've seen in some of the other talks, like a killer whale whistle, and you develop a really successful detector at that signal of interest. And there's very much a place for that research, but in a lot of the world, we know the species we're interested in, but we don't have a well-defined acoustic repertoire for what that species is or how we define those features. And within that frequency band of the species that we're interested in, for example, delphinids in my work, you have these other contrasting components of the soundscape. And with the binary idea of detecting the signal of interest versus not detecting it, you kind of throw away a lot of the ecological information in the soundscape within the background noise, such as vessel presence or whatever else might be happening, seismic surveying, and you hold on to what you have defined as information. So I'm kind of interested in this idea of, well, what is the information and what else can the acoustic data be telling us, as opposed to just there is a dolphin there or there isn't a dolphin there. So my work sits within the COMPASS project, which is a long-term passive acoustic monitoring project in the west of Scotland. It has 12 long-term monitoring buoys around the Scottish coastline and reaching down to Northern Irish waters. It's a very coastal region with a max depth of around 250 meters. And they've been collecting passive acoustic data since 2017. This is a hotbed area for marine mammals, particularly the delphinid family. But one of the key problems in this area is that although we kind of know what delphinid species we expect to find there, we don't have well-defined repertoires for the species. So in the lack of ground-truthing visual accounts of these species, you can't categorically say what species was there based on their acoustics. And hopefully in future, this will become something you can do, but at the moment it's not possible. And so anywhere you can see on the map that has the striped masking is a marine protected area. And the marine protected areas in the region are designated for multiple reasons, but some of which are designated for different delphinids. And so passive acoustic data is able to inform policy and marine management on how those marine protected areas are operating. if we're able to pull information out of the acoustic data that encompasses not just the species being there or not being there, but what else might be there at the same time that could impact whether this area is actually working for the purpose that it's working for. So it's not an easy question, but it's something that I felt machine learning could help address. So as I said, we have 12 acoustic monitoring stations. In my work that we're presenting today, we're just going to focus on these 3. So as I talk through the training data, keep a note, we're looking at the sort of northern edge, the western offshore Stanton Banks region, and then Garvelax is quite an interesting site. It's quite deep water, but it's right in the middle of a really busy, well, I say very busy, for the west of Scotland, very busy shipping area in terms of passenger ferries and cargo, etc. So 3 really different niche soundscapes across this array. And in future work, I'll incorporate the other data, but this is just what we'll focus on today. So to start the question, this is a big area of research. So we kind of started with what are the broadest categories that we can define that would allow us to get a model of this kind of caliber working. So for, if you were to apply this to your own work, the categories you might define might be slightly different. But for the COMPAS network, the chosen categories were ambient noise, which is really the absentee of the signal in any of the other categories. But within that ambient noise category, you get this range of geophonic noise and different fluctuations in how that background information might change, especially seasonally and temporally. So this is quite a fluctuating category of the sound source. It's not a static, I guess we normally would say it was like a negative class, but it still holds information that can be useful if you're maybe using this model to pull out sections of sound that could elaborate to a more soundscape oriented question. We then looked at delphinid tonal. So that would be any kind of tonal signal a dolphin emits. Anybody who's worked with them knows there's many different types of signal that they can produce. And so we didn't go into like signal type or, classify the different whistle shapes. This is purely, if there's a whistle there, there's a delphinid. Biological clicks is the class that incorporates burst pulse clicks and echolocation clicks. And then vessel noise. And vessel noise is whether a ship is passing, is starting to approach, which obviously has a lot of variation in how that signal is received, echo sounders, anything that would be related to that class. And so you can kind of see as this question evolves, these signal types are highly variable. So the typical machine learning and signals processing pipeline where you might hand derive features that you think will be helpful to your model just becomes a completely obsolete task. So the world of deep learning is quite nicely oriented to answer this question and account for the variation in signal types that we are looking to detect. So the next step of the work then is to develop the training set. So developing a training set for this type of question is somewhat complicated because you need to ensure that you're encompassing all kind of variation in the ambient noise spectra that could mask what signals you're then able to detect. If anyone's, we can get into that in a little bit. Basically, I looked at the COMPAS data itself forms a large part of the training set. And I should note there's no associated annotations with this data set. So we were starting from scratch in terms of labeling, which is quite a tedious task. And the idea for this research is that this could be quite a nice pipeline for anyone to implement for a small scale question. And so we wanted to also use other data sets that are out there and available and use them in combination with our own data that we're going to label. So I spent a long time manually labeling portions of the COMPAS data set, mainly forming the ambient sound source class. They're also in all of the other classes, but you'll note ambient noise purely comes from COMPAS. And that's because the ambient noise of your specific site is quite niche. And I wanted to make sure the model wasn't learning to define certain sound sources based on the ambient noise in other data sets. So that was a key component of our work. The other two DCLDE data sets are open source, available online, part of the DCLD conference series. So we used their 2011 Oregon data set, which is oriented to detect dolphin whistles. They have a really nice semi-labeled, I would say loosely labeled data set. There's a dolphin in the file, but you don't maybe know where. And then we used Hawaii, which is a really nice wide scale data set encompassing lots of different sound sources as well as delphinids. And then Sandown Bay is a location off the Isle of Wight in the UK. And we have some in-house data from lots of ship passing of different scales of vessel sizes. And that was used to bulk up the vessel category. But again, it's in a UK water system, so it shouldn't have too much of a effect on what that ambient noise detection is. But the key thing here is that we wanted a variation in the sampling rate of the data being collected, the temporal scale across the year of where the data is being collected from, so that background noise isn't static for a single signal type. Geographic region was varied purely on where we could get the label data from. And then within this, there's also a variation in the recording platform. So things like the sound traps, some of them were collected from static moorings, some were collected on board ships as I think the Hebridean Whale and Dolphin Trust charity data is like a hydrophone dipping system off a sailing boat. So all those kind of things that kind of vary how the signal is recorded and shown in the spectrogram, all those little variations are encompassed in our training set. So I think we in total had about 13,000 labeled data clips across the 4 sound sources. And then I used some augmentation methods to bulk these up. So augmentation is a tricky one with audio data. I don't think any of the image augmentation methods are super useful for this case study. So I used audio-based augmentation only. And so you've got raw audio, which is the audio obviously unchanged. Then we used a pitch shift augmentation. We altered the signal to noise ratio, and we also put in a time shift element. And these are all really small parameters that we're editing the file by, just to give a little bit of variation, but we didn't want to, amplify it so much that it becomes so unrecognizable to anything that the system really needs to detect, because this is just a small scale case study model. And also things like time shift, we didn't want the signal to become out of frame because of the way I labeled the data. I never time centered the signal in the image, so it could be on the very edge of the image. And if you time shift too far, you'll completely lose what the model is trying to learn, and you'll actually end up confusing your model during training. So augmentation was a threefold process. So by the end of this, we had about 39,000 image clips to train the model on. In terms of what we fed into the model, this is kind of niche to our work. So we had two-fold approach. There's just the normal linear spectrogram, and we processed them at 3 different FFT sizes, which was 1024, 2048, and 4096. And this was to try to account for the fact that each of these sound sources would be visually represented in a slightly different window size if you were looking at a model that could detect them individually and not together. And that was another kind of form of data augmentation almost, by feeding the model in something that was processed under different FFT parameters. But then the second input, which we tried and tested, and I'll show you the results for, but works much better, is we formed this stacked RGB image matrix. So typically an RGB image has 3 color channels, but what we did was we fed each of the FFT processed matrices into each color channel. So the model is seeing each signal represented at a different scaling. One thing that was really important here is that the frequency increments and the time increments are standardized across all of the data sets, regardless of the sampling rate. So that's one of our big pre-processing steps, is to make sure that's all completely standardized. And then once the matrix is formed, it's exported in a secondary step to make sure it retains the 224 pixel size without losing any information in that frequency and time increment bin step. So you get this nice little packaged 3-fold piece of information for the model to learn from, and it still thinks it's getting an image, but it's getting 3 times the information that it would have got otherwise. So by this stage, we have our input type, we have the training data, we know we want to ask it, so it's time for the model. So convolutional neural networks are pretty standard use case now in bioacoustics. When this work started, they kind of were, but transfer learning was becoming more and more the method of choice. And we didn't have a large training data set, so train from scratch would probably lead us to just a really overfitted model. So I chose to use the EfficientNet base model, which has quite niche methods of model scaling to make a very compact CNN architecture. It takes up very little space. I think our final train model is about 23 megabytes. And that's purposeful because one of the goals of my question is, could you build a model that's scalable to an on-platform device, such as a glider or an unmanned system? So I didn't want to use one of the big VGG or ResNet networks that are huge. And EfficientNet doesn't really lose. There's not a huge trade-off in accuracy by taking this smaller model. So I kept the weights and biases of the original model frozen up until the classification layer. And then the final 800,000 trainable parameters in the classification layer are retrained on our data set. And we use an output that gives a per class probability, and the threshold is based upon which class it belongs to. So then training was done in Google Colab, which is an open source platform. It means you don't need a GPU or a TPU. You can use one of theirs. I really recommend that for anyone who's experimenting with deep learning. And then the offline metrics were computed just in Python. So just to go through the results, you can see here at the top, we have our normal spectrogram input, where you give it different spectrograms at different FFT sizes versus our kind of niche stacked spectrogram input. So the results are pretty clear for themselves. Our average is 94% versus 80 with the combined spectrogram, and per class performance is really the key thing to take away here. Per class performance is much higher using the stacked spectrogram input. And so that became our use case for the rest of the model. We have quite nice false positive rates using the combined spectrogram input, and the model was able to perform really high across all the classes, particularly biological clicks, which you might remember from the training data graph is quite imbalanced in terms of its data set. So that was a really nice outcome for us. The second way we then decided to test the model was giving it the high and low extremities of signal to noise ratio. So we had a test set computed for signal to noise ratio of signals that are above 10 dB. And on the flip side, signals that are less than 10 dB in respect to signal to noise.
Just a couple minutes left.
Thank you. Performed really well at high signal to noise, which is pretty expected. So, if it didn't perform well there, we'd have a bit of a problem. All of our accuracies were above 95%. I think vessel noise was slightly lower at 90, but one of the issues with vessel noise that I think is hard to define is at what point is a vessel ambient noise and vessel noise? Like, when does that change happen? And that's something I'm sort of working on at the minute, and hopefully will amplify that accuracy. The low signal to noise ratio is super interesting because it still performed really well, and it outperformed actually a lot of manual annotations that had been made, and we had to go back and check and find out, oh no, actually the model's right, the signal is there. Biological clicks underperformed slightly, but again, the imbalanced data set could be the reason for that. And low signal to noise clicks sometimes can cause where we split the file based on the 3-second time frame. You might get one click on one side and a couple on the other, so it's not a nice train. And that was one of the issues around misclassifications that's kind of being worked on. And then the final part of my talk then is just how we looked at the model in terms of extremities in the ambient noise frame and how that background noise change might affect the model performance across different seasonalities. I think this is a really important takeaway actually in testing your model at the extremities of weather. You might have a really nice model that works in June when everything's nice and peaceful and calm, and you've got a really isolated frequency band you're interested in, but when those adverse weather conditions come along, is it going to perform as well? And so this kind of figure just gives you a nice overview of how varied our compass array is in terms of its ambient noise spectra. And, it's not a nice quiet site. There's a lot of different fluctuations happening seasonally, and this is a nice challenge for our model. And I've highlighted the bins that are, or the sites that I used in training and testing. So the results, interestingly, for our model, we found that the model was less successful in
1 minute.
Thank you. Suppose higher pressure weather conditions versus low pressure. And I think that might be due to other sound sources occurring, such as high biological activity in the low frequency area that I'll happily talk about in the breakout rooms. But overall, accuracy is still above 80% for such a small scale model training. And then low pressure, again, we had quite interesting results that just demonstrate you really need to understand the environment that you're going to deploy your model on. But above all, we had nice high accuracy and false positive rates across all classes, with different issues arising around vessel noise when it's being masked by geophonic activity. So I'd happily talk to you a little bit more about this in the breakout room, but if you do have any questions, I don't know if I can take them now. I don't know if that's allowed or if we have to wait.